Hello everyone. So in this video we are going to deal with these questions. So the very first question is rank the following species in order of the best nucleophile to the poorest one. So suppose this is my first one. Give me 1 second. Suppose this is the first one, this is second. Okay. First, this is second, this is third. And this is methanol, which is a solvent here. We have done in the class, this is polar protic solvent. So whenever we have a polar protic solvent, then do not think too much. Always follow the normal trend. It means whenever you are moving left to right in a periodic table, electronegativity increases, nucleophilicity decreases. And negative charge would be a stronger nucleophile than lone pair. So they all have negative charge. And they have different donor atom. So here we have two kind of donor. One is oxygen, one is sulfur. Oxygen and sulfur belongs to same group. And if you move down the group top to bottom, size increases, nucleophilicity also increases. Okay. So second would be the most stronger nucleophile because of the size. And now they both are negative. So same donor atom, both have oxygen. Now the next thing is resonance. This one is without resonance, this one is in the resonance, you can see. So resonance decreases the nucleophilicity. So second, third, and then first. So it would be the correct order. In the next one, DMSO is a polar aprotic solvent. But because oxygen is a donor here, so do not think too much about the size because we have the same donor atom. Now look at the resonance. There is no resonance here, non-conjugated. And this is conjugated, it means resonance. So you know that resonance decreases nucleophilicity. So if this is first, this is second. So this one is my stronger nucleophile. So second greater than first. The third case, methanol is again polar protic solvent. And here the donor atom is oxygen and here nitrogen. Hydrogen is not donor, okay? So if you look at the periodic table, the elements are arranged in this way, BCNOF. So here we have nitrogen, here we have oxygen. You know that on moving left to right, electronegativity increases, nucleophilicity decreases. So oxygen have greater electronegativity. That's why low nucleophilicity. So nitrogen have stronger nucleophilic strength. So this is my first, this is second. So second greater than first. In the D, again we have a polar protic solvent. And this is bromine, chlorine and iodine. Whenever polar protic, always follow the normal trend. You know that elements are arranged in this way in a group. So top to bottom, size increases, nucleophilicity strength also increases. So iodine minus, then Br minus, and then Cl minus. That would be the correct order. Which number of each pair is a better nucleophile in methanol? So methanol is a polar protic solvent. So OH minus and H2O, same donor atom, oxygen, oxygen. You know that negative charge is a stronger nucleophile. So this one would be the stronger nucleophile. Here nitrogen and oxygen, you know that low electronegativity, better nucleophilic strength. So nitrogen is a better nucleophile. Oxygen and sulfur, polar protic solvent. Size increases, nucleophilicity increases. So H2S is a better nucleophile. Same concept. Both are negatively charged. So again depend on the size because here oxygen is donor, here sulfur. So sulfur would be a stronger nucleophile. Here iodine would be a stronger nucleophile because iodine have a bigger size, And here bromine, because if you look at the halogens positioning, so down the group size increases, nucleophilicity increases. Clear? Next, arrange them from the best to poorest nucleophile in aqueous solution. So aqueous solution means it is not mentioned here polar protic or aprotic. So whenever the nature of solution is not given, always assume polar protic solvent. Okay. So look at here. Negative is always a stronger nucleophile than the lone pair. So sulfur negative, oxygen negative, oxygen negative, oxygen negative. This one is a neutral. So if I am going to mark 1, 2, 3, 4 and 5th. Now oxygen and sulfur, here we have two kind of donor atom, oxygen and sulfur. Both are negatively charged here because negative is a stronger nucleophile. And now if you look at the positioning, oxygen and sulfur belongs to same group. So down the group size increases. So sulfur is the best nucleophile. So 5th. Now between 1st, 2nd, 3rd and 4th, the third is, 1st, 3rd, 4th and 2nd, they all have same donor atom, oxygen. Now the deciding factor is resonance. So 3rd have no resonance, so it should be the stronger nucleophile. Now 1st, 2nd, 4th. If you look at the resonance in the 1st and 4th, 1st have like unequal resonance, while the 4th have equal contributing resonance structure. So equal contributing resonance structure means stronger resonance. Stronger resonance means nucleophilic strength should be low. So 1st, then 4th, and in the last the neutral one, 2nd. So better the resonance, poor the nucleophilicity. 4th have better resonance because once you draw the resonating structure, negative is again over the oxygen. So in both the resonance structure, negative charge delocalize over oxygen. But in the first one, if you are going to draw the resonance structure, the negative is going to delocalize over the carbon atom. So we have two unequal resonating structure. 4th have equal. I can say equal resonating structure. So equal resonating structure means nucleophilicity decreases. Now the next is identifying whether each of the following will function as a nucleophile and electrophile. So we have done this already in the class. I said that generally positive charge species acts as electrophile as well as incomplete octet. While in the nucleophile, the negative charge and lone pair. So look at this one. This is a polar bond. Bromine is a more electronegative. Carbon is less electronegative. So this carbon is a delta positive, which means it would act as an electrophile. So polar bond means the less electronegative would behave as electron deficient, and that can be considered as electrophile. Now here oxygen have the lone pair, so this is a nucleophile. Now CO bond, this is delta negative, this is delta positive, so this carbon would act as electrophile. Here double bond is always the nucleophile. Here carbocation, always electrophile. This is O minus, again nucleophile, because negative charge and lone pair can act as a nucleophile. Sodium is plus, Br is minus, so this minus means nucleophile. LiOH, again Li plus OH minus, so this would be my nucleophile. CH3I is a polar one, so iodine has more electronegativity than carbon, so it would be my electrophile, the carbon part. You can say the negative part can also act as a nucleophile in polar one. So like here, this is CO, so this oxygen can act as a nucleophile and carbon can act as a electrophile. In this case, if you draw this structure, this is oxygen bonded to a carbon, and this carbon have three tertiary group, methyl, and this is O minus K plus. Because metal, if bonded to any atom like this A, So metal always be positive and A will always be negative. So this would act as a nucleophile. So this oxygen minus, the entire oxygen minus part would be act as a nucleophile, and oxygen is here acting as a nucleophilic atom. For each of the following carbocation, determine if it's likely to rearrange. If so, draw the rearranged carbocation, the most stable form. Right now here we have number of alpha H. How many alpha H here we have? So this is the alpha carbon. This one is the alpha carbon having 2H. Here 1. So it has 3 alpha H. So if you're going to shift the positive charge in the right hand side at tertiary position, suppose here. So it would be this. So the number of alpha H increases here. Alpha, alpha, alpha. So 3 to 5 to 7 alpha H. So this would be the more stable, and this is called 1, 2 hydride shift. Okay. Now the next B. Right now this is alpha, alpha, alpha. So 3 to 5, 6 alpha H. And if you are going to shift the positive charge at this position by hydride shift, so 3 to 5 and 1. 6 alpha H here as well. So no rearrangement because it already is stable. In this case, this is very important case basically. At this position we don't have any alpha H. So we can shift the methyl group. So if you are going to shift a methyl, so now you can see this is 1, 2 methyl shift. At this position, this carbocation is not in resonance, but here it is a part of resonance, and resonance increases stability. So this one is a stable one. So this would rearrange into this. Number of alpha H here 4. If you rearrange this carbocation in the right hand side or left hand side, the number of alpha H remains same. So no rearrangement. In this case, we have 3 and 1, 4 alpha H, and if we are going to shift a hydrogen from here into this position, then the alpha H would be 8. So this one is a more stable carbocation, and this is called 1, 2 hydride shift. So this is going to rearrange into this. In this case, we have 3 alpha H only because this alpha carbon have no hydrogen. So if we are going to shift any of the methyl, so alpha H increases 3, 3, 6 and 1, 7 alpha H. So it would rearrange. This is called 1, 2 methyl shift. In the next one, here we have hydrogen. So one of the hydrogen we can shift. So this is the resonance stabilized carbocation. This is called 1, 2 hydride shift. So it would rearrange. And the last case, how many alpha H here? Alpha, alpha, alpha. So 3, 1, 4, 1, 5, 5 alpha H. So if we are going to shift the carbocation, like hydride shift, so how many alpha H? 2 to 4, 5. You can see. If you are going to shift positive charge at this position, then we have 5 alpha H. There is another chance if we can shift the positive charge at this position. So we have this carbocation. This one. So here the number of alpha H increases. Why? This is CH3, this is CH3, this is 1. So alpha, 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 3, 3, 6, 7 alpha H. So this would be the correct rearranged form. This is called 1, 2 hydride shift. So this rearrangement would not be possible. The bottom one is correct one. So this is all about this worksheet. Thank you so much everyone.